All right, so here we are for Electrostatics Worksheet 3, Coulomb's Law. Take a look at the last problem in the packet, which is this one. It says, hey, we've got three charges placed as shown below. Looks like they're at the corners, three of the corners of a square. That's 3 meters on a side. They say determine the magnitude and direction of the net electrostatic force on charge Q1. So we want to see the size and direction of the total electric force on this guy. As part of the solution, include a force diagram of Q1. Of course, we're going to draw a force diagram for Q1. We're trying to find the total force on it. All right, so here we go. Again, I'm going to transfer the diagram to my paper because I like to have the diagram right there with the work instead of on a separate sheet. So bear with me as I sketch this over. All right, so let's see, we're doing question 10. All right, so I've got my charges here. Blunk, blunk, blunk. Okay, like the corners of a square. Good enough. Okay, 3 meters, 3 meters. They tell me the charges. Now I notice that this charge is positive, this charge is negative, this charge is positive. I could go ahead and label that. Plus, minus, plus. Okay. Take a look at this. You say, well, they tell us that this is this guy is charge Q1 that we're trying to find the total force on. This one up here is Q3, and this is Q2. All right, we know, take a look at this, you say, look at the forces on Q1, you say, okay, Q3 and Q1, those are both positive, so they would repel each other. So this is gonna get pushed directly away from that other positive. So like, if I kind of drew a line, it's gonna get pushed directly away along that line. So this here is my electrical force on charge 1 by charge 3. This one, on the other hand, is negative. Negative and positive opposite charges, they'll want to attract. So Q1 will get pulled along the line towards Q2. There'll be an electrical force on Q1 like that. This is the electrical force on Q1 by Q2. All right, and that's it. That's my electrical forces on Q1. So now you say, okay, can I find the size of these forces? You say, well, of course I can. I'll just use Coulomb's law. So you say, I know that Fe is K, Q1, Q2, over that distance squared. Okay, but now I want to look at this one. Let's say this is the electrical force on 1 by 3. So to find on 1 by 3, this will be Q1 and Q3, and that distance will be the distance between 1 and 3. It's being squared in the denominator there. I'll do, and I can put my values in because I have values for all those things. K is 9 times 10 to the 9. Q1 is given to be 4.5 times 10 to the negative 5 coulombs. And Q3 is given to be 1.8 times 10 to the negative 5 coulombs. And that separation distance, that's the distance between the middles of these charges. Hopefully you recognize, look, 3 meters, 3 meters, it's a square, so it's a right angle. You recognize this is a 45, 45, 90 right triangle. And we have a side length of 3, so hopefully you recognize that hypotenuse will be 3 root 2. You can figure it out. So this distance here is 3 root 2 meters. So that's the distance. That's the denominator. It's 3 root 2, and that's going to be squared. Let's go ahead and I'm going to go ahead and get a value for that. All right. Yep. Let's get a value for that. So I'm going to do all my coefficients. So I'll do 9 times 4.5 times 1.8 divided by 3 root 2 squared. That would be like 9 times root 2 squared is, so it's, 3 squared times root 2 squared. 3 squared is 9. Root 2 squared is 2. 2 times 9 is 18. So divide by 18. And when I do that, I get 4.05. And your power is a 10, 10 to the 9, 10 to the minus 5, 10 to the minus 5. That's just 10 to the first power. So that'll come out to be just 40.5 newtons. That's the force in the X. That's F13. Okay. Electrical force on 1 by 3. Okay. Now let's figure out the electrical force on 1 by 2. So you say, again, I'm going to use Coulomb's law. That'd be K, Q1, Q2, over that distance from 1 to 2 squared. Well, the distance from 1 to 2, that's just 3 meters, right? Let's put our values in. 9 times 10 to the 9 times Q1 is 4.5 times 10 to the negative 5. Q2, that's this guy. That was 1.2 times 10 to the negative 5. The distance between 1 and 2, that's just 3 meters. All right. Doing this one in my calculator. Again, I'm going to do all the coefficients. So I have 9 times 4.5 times 1.2 divided by 9. Which gives me 5.4. And then I've got 10 to the 9, 10 to the minus 5, 10 to the minus 5. That just comes out to be 10 to the minus 1. So if I got 5.4 times 10 to the minus 1, that'll be 0.55. That's a pretty big difference between the force. I think I made a mistake somewhere. Nope. No, that's quite all right. Yeah, pretty sure. That seems crazy that force would be that much bigger than that force. I think I need to double check. I'm sorry. Doing this late at night / early AM. I need to get some sleep. If I run through this 9 times 4.5 times 1.2, yeah. 10 minus 5, 10 minus 5, yeah. Okay. And then 3 meters of distance. I guess that makes sense. Maybe I need to double check this one. 9 times 4.5 times 1.8 divided by, well, that seems to, this is 10 to the minus 1. So I put that the wrong way. This should be 0.405. I'm sorry. There we go. 0.405, 0.55. Okay, there we go. That's right. Okay, so I found those two. Okay, so got it. So these are the values. There, no one would ever know. These are the values for those two forces. Okay, now I know how big this diagonal force is here. I know how big this horizontal force is here. Now, how do I find the total? I need to add those vectors together. And the key part, these are arrows I'm adding together. So you're like, well, gosh, it's been a while since we had to add vectors that were at weird angles to each other. It's easy to add arrows when they're going this along the same axis. Everything going left, right, or everything going up, down, right? And we can even add them if they're at right angles to each other. We just make a new triangle and use Pythagorean theorem. But these are at weird angles to each other. What do? We're going to replace them with components. So let's say we do coordinate axes left, right, up, down, x and y. Let's call up and right positive. Then I'm going to replace these vectors with their components. Fe13, I'll split that up. I'll make a chain of arrows that starts where it starts and ends where it ends. But it's going to be arrows going along the axes to show my components. So dot, 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 dot. No. This is the horizontal, the x and the y components of Fe13. You say, hey, these components, how do I calculate them? I'm going to need an angle. You say, well, conveniently, this angle here, I'm going to call it theta. You say, hey, look, this line continues, this line continues. That's this angle, right? Same angle. And remember, this was a square cut along the diagonal, so this is 45, 45, 90. This is half of the 90 degree, right? 45. And so you say, oh, okay, so that theta is 45. So how big is this side going to be? This is the adjacent to that, so that'll be the hypotenuse, Fe13, times the cosine of 45. And this will be Fe13 times the sine of 45. And while for 45 degrees, sine and cosine are equal, if this was a slightly different shape, like a big rectangle or something, this angle would not be 45. And I would have to do some calculations here with this triangle to figure out the angle. But anyway, but there we go. So I'm replacing this arrow with these. What about this one? Do I have to split this one into components? You say, no, it's already going along the x-axis. You don't have to break into components at all. So I am, instead of to add these two red arrows, I'm going to replace this one by components, and I'm going to add these three arrows together. How does that work? Well, we're going to find the sum of the forces now in the x-axis, right? And so you say, well, my force is in the x-axis. I'll have Fe13 cosine 45 going to the right minus Fe12. Go on the right, make that positive, minus Fe12. All right. And I have all the values I need because I already calculated Fe13 here, and I calculated Fe12 here. I just plug those in and find that total force in the horizontal axis. If we do that, that will come out to be Fe13 is 0.405 cosine 45 minus Fe12, 0.55. Sure, why not? We'll do the math. We'll finish that one up. So if I did that, I would take 0.405 cosine 45 minus 0.55. And if I do that, that gives me a value for the total force in the x-axis of a negative 0.264 newtons. You're like, what's going on with that? You say, well, it turns out this horizontal force here is bigger than this component here. So the total ends up being to the left. All right, so that's my horizontal force. Now I want to find the total force in the vertical axis. So I'll do the same sort of thing. I'll do the sum of the forces in the vertical axis. Okay, and you say, well, and yep. And if I did that, it'd be forces up minus forces down, because I called this quadrant positive. You say, well, going up, like, wait a minute, I don't have any charges shown pulling up on this guy. But I do have this component going down. So the total force up and down would be just minus Fe13 sine 45. So my total force in the y-axis is a negative Fe13 sine 45. Okay, conveniently Fe13 we solve for over here. We're ready to just go ahead and plug and chug in our mass. I'm sorry, go ahead and plug in our value for the force and solve for that. If I go ahead and do that in my calculator, I'll be taking 0.405 times the sine of 45 degrees. And if I do that, I'm going to get negative 0.286. Now, if I do that, I've got so you notice this comes out to be negative. That's because it's tugging down in what we call the negative direction here on our coordinate axes, right? Okay, hey, what we're trying to find now is the total force on Q1. We found the two electrical forces that were acting, and then we split them into components, so that now we can take the total horizontal force and the total vertical force. What do I do once I have those? Well, now you say, well, forces in the horizontal axis and forces in the vertical axis, they're at right angles to each other. And that means I can make a new triangle, a right triangle, which means I can use the trig functions and find that total force by finding the hypotenuse of this new triangle. So basically what I'm going to do, I'm going to make a triangle with these being two of the sides of the triangle, the two legs of the triangle. So let's see. This came out to be negative. It means it's going to the left, which means this was bigger than that. That's okay. So I've got this negative 0.264, and the vertical, I've got 0.286 going down there, yeah? Okay, and my goal is to find the total. This and this is the same as just doing that. So use the little Pythagorean theorem. Oops. 0.264. And let's find the hypotenuse first. I'll go ahead and I'll square that and square that, take the square root. Doing Pythagorean theorem. This is the total force. Right now, let's find its size by using Pythagorean theorem. So I would get that total force I'm going to use Pythagorean theorem. Sorry, a squared plus b squared is c squared. So I'll be doing that 0.264 squared plus 0.286 squared. Right, and that should equal that hypotenuse squared. So running through, again, I can do this because it's a right triangle, because we chose to break these things into x and y components, and x and y are right angles to each other. Okay, so my total force, here we go, 0.264 squared and 0.286 squared. And what I get is 0.151 newtons. Now that I have the total force, okay, all right, and this is a good time to check my answer before I go any further. And I noticed that my answer is different than the answer on Wishway solution set. I suspect it's because I'm sleepy and I'm probably made a dumb mistake somewhere. And you guys have probably seen it before and you've been yelling at the screen, hey, you made that mistake there. I'm pretty confident that these I did right. Then when I do this, I'm doing my FE13 times cosine 45, yep, minus FE12, which is 0.55. That makes sense to me, right? So 0.264 squared. This is backup step. 0.405 cosine 45 minus, oh, I bet I know what I did. No, that's right. 0.263. Yeah, 0.2636. Yep. No, that comes out right. Those are the right values for those. And the x-axis, it makes sense that I'm doing FE13 cosine. Yeah, we're all good. Okay. Well, anyway, now I want to find my total. So what I'm doing here, sorry, just to make that clear, I'm taking on this side, this is the total force in the x-axis, and this is the total of all the vertical forces. total force in the y. Okay, and then oh wait, you know what I did? I forgot to take a square root at the end. Okay, so we're doing this side squared plus this side squared, and then take a square root to get the hypotenuse. So I'd be doing 0.264 squared plus 0.286 squared. And you say, adding those together and taking a square root. Okay, I just forgot to take a square root at the end is what I did. Because this squared plus this squared equals this squared. To find this, I got to take a square root. So it's the square root of that 0.151, which came out to be 0.389 newtons. Ta-da! Okay, but that's not quite it. We found the total force. Now we want to know what angle it's at, right? And so to find, let's say, this angle, you say this is the adjacent and this is the opposite, these two sides we were given. And so you say, oh, okay, I'll use an inverse trig function, inverse tangent in this case. Say tangent is opposite over adjacent. Let's do an inverse of that to find those side lengths. So, or rather the angle. And so you say, all right, where is the room on my page? I really ought to go to another piece of paper, but I'm going to squeeze it in here. That's really, really poor form, Dave. Let's use another piece of paper to finish this up. So if I do this, you say, now I want to know the angle. So I say, hey, that angle is going to be an inverse tangent of the opposite. That'll be the sum of the forces in the y over the adjacent side, sum of the forces in the x. Okay, so one inverse tan of total force in the y came out to be that negative 0.286. And the total force in the x-axis ended up being negative 0.264. All right, and I can punch that in my calculator. All right, if I do that, second to get inverse tangent of the quantity. All right, and recognize that I'm just going to take, I got a negative over negative, so it's going to make it positive. So I'm not going to bother with the negative signs. So I'm going to do 0.286 over 0.264. And this gives me an angle for theta. It says 47.3 degrees. Recognize that is below the negative x-axis. So really, I would probably want to, with my coordinate system, I probably want to go add 180 to that measurement. So if I did that, that's actually a value of 227.3 degrees. All right, if I'm heading, I'm sorry, so 227.2, so that's which way it's going. All right. All right. Hey, does that match what we've got here? Yeah, within a degree, but it's about a degree off from which way's answer. That 0.383 newtons, I got 0.389. So yeah, same answer. We are all good. Okay, so my final answer, the total force is 0.389 newtons at an angle of 227.3 degrees. Right, starting here, going around like that. Okay, and that's that total. Okay, and that is problem 10. Okay, so once again, use Coulomb's law to find your forces, do a nice clean diagram so you can see what's going on, break into components, find the sum of all the forces in the x-axis, right minus left, find the sum of all the forces in the y-axis, up minus down. And once you've got those two, the sum of the force, all the force x components and all the y components, now I get to use Pythagorean theorem with the total x and the total y to solve for that sum of both of them, that vector sum, which I do by Pythagorean theorem. And once I got that, I want to know the angle it's at, so I solve for that with trig function, inverse trig function. All right, that's it. That's problem 10.